vector multiplication. We're looking at the scalar or dot product. The result of a scalar product is a scalar quantity, and we use a dot to represent the multiplication between two vectors A and B. If we have a vector A pointing in a given direction, a vector B pointing in another direction, the angle between the directions of A and B is phi. Vector or cross product, the vector product or the cross product gives us a result which is a vector quantity. So A cross B gives us a vector quantity, oftentimes referred to as a pseudo vector. We'll talk some more about that later. Now the scalar or dot product gives us the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. If we write vector A pointing to the right, vector B pointing at some angle phi away from A, then we can see that the projection of vector B onto vector A is B cosine phi. We see that we form a right triangle here with the hypotenuse being the magnitude of B, then this side is B cosine phi. Similarly, if we project A onto vector B, we can see that the projection of A onto B is this side of this right triangle, where now the hypotenuse is the side A. We have A cosine phi. So we can write that the dot product is A times B cosine phi, or B times A cosine phi. Either one of these gives us the same thing of AB cosine phi. So we notice then that B is the projection of vector B onto vector A, or the scalar component of vector B in the direction of vector A. And A cosine phi is the projection of vector A onto vector B, or the scalar component of vector A in the direction of vector B. So we see again vectors A and B. So what we mean by the direction of A is a unit vector, call it A hat, which has a magnitude or length of 1, but the same direction as vector A, and a vector B hat, which has a magnitude of 1 and is in the same direction as vector B. So again, writing A dot B, the dot product of A and B, as A times B cosine phi, if we solve for B cosine phi is then A dot B divided by the magnitude of A. But the magnitude of A in the denominator and in the numerator, the vector A, gives us the unit vector in the direction of A. So anytime we want to find, in general, a unit vector in the direction of a given vector, we take the vector itself and divide it by the magnitude of that vector. So this gives us the unit vector in the direction of A. So we can write that B cosine phi is then B dot unit vector A. Also, we can write that the dot product of A and B is equal to B times A cosine phi. If we solve for A cosine phi, we get that A cosine phi is equal to the dot product of A and B divided by the magnitude of B, or since the vector B divided by its magnitude is simply the unit vector in the direction of B, or B hat, unit vector B, we can then write, as an example, if we let A be equal to 3.0i plus 2.0j minus 3.0k, and B, the vector B, is 2.0i plus 3.0j plus 5.0k, we'd like to A, find the scalar component of B in the direction of A, B, find the scalar component of A in the direction of B, and C, find the angle between A and B. So to do the first part, the scalar component of B in the direction of A, so this is already telling us the direction of A, so we pick the unit vector in the direction of A with the vector B. So the scalar component of B in the direction of A, let's do that first. So what we have then is the vector b in the direction of A. Remember that this is b dot A divided by the magnitude of A. So we write then vector b, which is 2.0 I, we said, plus 3.0 j plus 5.0 k. That's vector b dotted into vector a, and vector a is 3.0 I plus 2.0 j minus 3.0 k, and we divide the whole thing by the magnitude of a, and a is 3i plus 2j minus 3k. So we take each of the components, we square them, we add them together, and then we take the square root as we usually do. So this gives us the square root of the sum of the squares of the components of vector A, gives us the magnitude. So here we have, if we only keep one significant figure for clarity, we got 2 times 3, we're multiplying this times this. Remember, I dot I is 1, I dot j is 0, I dot k is 0. So only I dot I, j dot j, and k dot k remain. So we got 2 times 3 plus 3 times 2 plus 5 times minus 3 divided by the square root of 22. And so this gives us 6 plus 6 minus 15 divided by the square root of 22, or b dot a hat is equal to minus 3 divided by the square root of 22, which is minus 0.64 to 2 significant figures. So our answer here then is minus 0.64. This gives us the component of b in the direction of A. Notice that it's negative and it's a very small number. We'll come back to the negative after we do the rest of the problem here, the example. The next part says find the scalar component of A in the direction of B. So we're going to take now A in the direction of B. So here in this part we've got, this is part B. Here we have vector A now in the direction of B. B hat is a unit vector in the direction of B, so this is A dot B divided by the magnitude of B. We already know what A dot B is. It's from before, from part A, it's minus 3. But now we need to divide by the magnitude of B, and this is 2.0 squared plus 3.0 squared plus 5.0 squared. We take the square root of the whole thing, and what we get here is minus 3.0 divided by the square root of 38. So this gives us then that A dot B hat, or the component A in the direction of B, is minus 0.49. Again, to two significant figures. And again, we see that this is a negative value. So what we had for the component of B in the direction of A, minus 0.64, the component of A in the direction of B is minus 0.49. And the last thing we need to figure out is the angle between A and B. The angle between A and B. So here, this was part A. And so part C now is the angle between A and B. We know that A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between the two. So we can solve for the cosine of phi, and this is A dot B over the product of the magnitudes of A and B. We already know what the dot product is of A and B. That's minus 3.0. We divide by the magnitudes of A and B. The magnitude of A is the square root of 22. The magnitude of B is the square root of 38. So this is minus 3.0 divided by the square root of 836. So phi is then the inverse cosine of minus 3.0 divided by the square root of 836. So phi to two significant figures is 96 degrees. Now remember what we said, that if the angle between the two vectors is less than 90 degrees, the dot product is going to be positive. If the angle is 90 degrees, the dot product is 0 because there is 0 projection. And if the angle is greater than 90 degrees, then the dot product is going to be negative. So we see that we got a negative value here and a negative value here for both dot products. That means that the angle between A and B is larger than 90 degrees, and in fact we get just slightly larger than 90 degrees at 96 degrees. Next, we talk about the vector or cross product. The cross product of two vectors A and B, again A and B with the angle between the two being phi, is given by the magnitude of the first times the magnitude of the second times the sine of the angle between the two, pointing in the unit normal direction, where n hat is a unit normal vector. That means it's perpendicular to the plane containing both vectors A and B. See here we see the vector A cross B. If you use the right hand rule, you take your fingers, point them in the direction of the first vector, in this case A, curl your fingers in the direction of B, and your thumb points in the direction of the resulting vector. So the cross product of two vectors is perpendicular to the plane containing the two vectors, or it's perpendicular to both A and B at the same time. Notice also that the magnitude of the cross product is the area of the parallelogram formed by sides A and B. To find the cross product of two vectors, we use the determinant form, where the first row has the unit vectors I, j, k. The second row has the components of the first vector ax, ay, and ac. And the third row has the components of the second vector, in this case bx, by, and bc. So what we do is we take, essentially, for the first component in the I direction, we ignore the first column and the first row, and we only look at the sub matrix made up of AY, AC, BY, BC. So we take AY times BC minus AC times BY. AY, BC minus AC, BY. Next, we take minus j, because it's the second column. The first column is positive, the second is negative, the third is positive, and so on. So they alternate in sign. Here, then it's a negative j. We ignore the first row and the second column and only consider ax times bz minus ac times bx. ax bc minus ac bx. And then we take k plus k. We ignore the first row and the third column, and we only consider this submatrix of ax, ay, bx, by. So we take ax times by, ax by, minus ay, bx, ay, bx. So let's look at the example where we have again the same vectors a and b. So for a cross b, then we form I, j, and k, our determinant. 3, 2, and minus 3 is the first vector components a, and then 2, 3, and 5. So those are the components of vector b. So what is this? We have a cross b equals, then I is going to be 2 times 5 minus a minus 3 times 3. So we got 2 times 5 minus a minus 3 times 3. That's in the ith direction. Next, minus j, and we have 3 times 5 minus a minus 3 times 2. And then plus k. For k, we have 3 times 3 minus 2 times 2. So putting it all together, we have 10 minus a minus 9. That's 19i. And then we have 3 times 5, 15, minus a minus 6. But that's 21 minus 21j, and then we have plus 3 times 3, 9, minus 2 times 2, 4, 9 minus 4, that's 5k. So let me do it like this. This will become then, this will be, take two significant figures, 5.0. Okay, so this gives us the cross product of A and B.